So, picking up where we had left off last time, we had come to a number of key conclusions that I'd like to review for you briefly, so that then we can move quickly on to our next topic, which actually is going to bring us to our first circuit, something we'll be enabled to analyze now that we have this very powerful concept of voltage. So if you recall what our main preoccupations were last time, we were thinking about energy. And we had defined, for instance, the potential energy of a system as the work needed for us to move a particle from a reference point to a particular point x where we are interested in its energy. So for instance, in my diagram over here, there's always going to be some reference point. This is this arbitrary point of zero potential that we always talk about. And then we're going to measure all of our energies relative to that reference point. So if we calculate how much work we do, the work done by us to move a particle along some path to take it from this reference point that we call zero energy to the point x, that work invested by us is energy then that is stored in the system that we could potentially pull back out later. That is the whole idea behind this concept of potential energy. So to calculate it, we calculate this work done by us. That work then is a standard work integral where you integrate from your reference point, the beginning part of your path, to the ending point of your path. You integrate then to calculate the work done by us, the force that we are imposing on the particle, F us. That, of course, is opposite the forces that the system itself are imposing on the particle so that we can force it along this path. That then gives us our final integral, our definition of work and potential energy from the standard mechanics point of view. The very next thing we did was to convert this into something that pertains directly to electricity. Excuse me. In particular, we asked about the work we would have to invest to move a charged particle of charge capital Q to carry it along a path from A to B. So here's my charged particle Q. I'm moving it between 2 points, A and B. We notice that the work needed to do that is actually directly proportional to the charge Q. And that proportionality constant then is a new quantity which depends on both the beginning and the ending point, points A and B. And that quantity that is proportional to Q, which is then the work per unit charge, if I divide it through by Q, that quantity is the voltage from point A to point B. We had emphasized that voltage is in fact a two-point function. You need 2 points to define it, a beginning point and an end point. And that actually comports quite well with the operational definition of voltage, which is that you take a voltmeter, and you will find that every voltmeter has a minus terminal and a plus terminal, which you then wire to the 2 points of interest before you then measure the voltage from point A to point B. The voltage that you read off will flip signs if you confuse the plus and the minus. So keep in mind the minus always goes to the reference point, the starting point, and the plus then gets wired to the final point, in this case point B. We then looked at our first application of this concept to the voltage associated with a point charge. So we had a point charge Q over here, and we had determined the voltage going from point A to point B, and through a detailed analysis, we were able to prove that voltage had the following formula. It depends on Coulomb's constant and the charge in direct proportion, and then it is just 1 over the distance from point B to the charge minus 1 over the distance from point A to the charge. The key thing that we were very excited by for this formula was the fact that the voltage then from a point charge is completely independent of the path that we choose to move our particle from some arbitrary point A to some other arbitrary point B. As we do that, the only thing that turned out to be relevant to it was these little changes in the radius. The dot product that's inherent in this definition produces a cosine factor so that the distances that we're traveling, the only important component of them are the ones that correspond to the changes in radius. Hence we had this formula that depended only on radius, distance from the charge which is creating the field. That's a very nice property because this path independence means that whatever work we put in to move a particle from the reference point to the final point, we can always get that amount of work back regardless of whatever path we decide to travel. Now, this is very nice because we have this nice path independent property established for point charges, but what about for general charge distributions? So to answer that question, we're now going to move on to our first main topic for this lecture, which is to figure out how we can take the voltages from a point charge and use those voltages then to give us results for more complicated charge situations. If you think about it and you guess about how we've done things for the electric field, you will quickly realize we're going to be looking at a principle of superposition.